Without electricity, it would be nearly impossible to operate a process facility. Electricity is used to run motors that drive equipment, such as pumps, mixers, and air compressors. Electricity is also used for lighting systems, instrumentation and control systems, and heating and air conditioning systems. Traditionally, electricity has been defined as the result of a movement of electrons from one place to another. The electrons come from atoms. Atoms consist of three basic particles: protons, electrons, and neutrons. Protons have a positive electrical charge. Electrons have a negative charge. And neutrons don't have a charge. When an atom has the same number of electrons as protons, the positive and negative charges are balanced, and the atom is said to be electrically neutral. There are many forces in nature that can upset the balance of electrically neutral atoms. Any occurrence that causes an electrical charge imbalance, or in other words, anything that causes the number of electrons to be different from the number of protons, creates an electrical potential. An electrical potential is a situation that can lead to an electrical discharge. When an electrical discharge occurs, electrons or electrical charges move from one place to another. One example of an electrical potential is static electricity. Static electricity occurs when a large number of electrons builds up on a surface. A common cause of this type of buildup is friction. The buildup of electrons on a surface results in a high electrical charge and, consequently, a high electrical potential. When the potential is great enough, the electrons move or flow from one place to another. This flow of electrons is referred to as an electrostatic discharge. One of the most dramatic examples of an electrostatic discharge is lightning. Lightning occurs when atmospheric conditions cause a huge electrical potential to be built up between clouds and the Earth. When the charge imbalance is great enough, a tremendous arc forms that we call lightning. Electrostatic discharges are situations in which there's a momentary flow of current. Current can be defined as the movement of electrons or electrical charges from one place to another. For the vast majority of electrical equipment, a continuous flow of current is necessary for the equipment to operate. Now, with either an electrostatic discharge or a continuous current flow, there's movement of electrons. In order for this movement to occur, certain forces must be present. The forces related to the movement of electrons can be referred to as electromotive forces, or EMF. EMF is one way of expressing electrical potential. Another term that is used interchangeably with electrical potential is voltage. There are many sources of electrical potential. In this part, we'll focus on three: chemical action, heat, and light. Chemical action is the source of electrical potential that's at work in batteries. Whether the battery is a throwaway type or a rechargeable type, the basic elements are a set of electrodes and an electrolyte. The electrodes are generally some type of metallic material that becomes charged as a result of a chemical reaction. The electrolyte is the chemical that causes the necessary chemical reaction. Before the chemical reaction begins, both electrodes are electrically neutral. That is, they have an equal number of protons and electrons. The chemical reaction that takes place in a battery causes electrons to leave one of the electrodes. When this occurs, the electrode becomes positively charged. At the same time, the electrons build up on the other electrode, which becomes negatively charged. The oppositely charged electrodes create an electrical potential. If the electrodes are connected as part of a complete flow path, the electrical potential will cause a flow of electrons or current. A complete flow path is commonly referred to as a circuit. Another source of electrical potential is heat. One device that uses this source is a thermocouple. A thermocouple basically consists of two dissimilar metals that are joined together. When heat is applied to a thermocouple, the electrons in the metals move in such a way that an electrical potential develops. If the thermocouple is connected as part of a complete flow path, current flow will result, as indicated on this meter. As more heat is applied, the electrical potential and the resulting current flow increase. Since the amount of heat applied to a thermocouple is related to electrical potential, and therefore to current, thermocouples are most often used as temperature sensors in process systems. A third source of electrical potential is light. Light may be a great source of electricity in the future. The principle of producing electricity by using light is referred to as the photoelectric effect. Certain materials will generate electricity when they're exposed to light. For example, a solar cell contains this type of material. In fact, this solar cell can produce enough electricity to run a small motor. When the light intensity is increased, more electricity is generated, causing the motor to turn faster. Now, although chemical action, heat, and light are all sources of electrical potential, they're not sufficient or economical enough to supply continuous power for running electrical equipment. However, in certain applications, they can serve as important emergency power supplies. When magnetic effects are used to create an electrical potential, three elements are necessary. They are a magnetic field, a conductor, and relative motion between the magnetic field and the conductor. Let's begin with the magnetic field. Magnets have two poles, which are generally identified as north and south. When two magnets are placed close together, opposite poles will attract each other, and like poles will repel each other. The magnetic forces that cause these actions are invisible. They result from magnetic fields around the magnets. We can get an idea of what these magnetic fields look like with a simple demonstration. First, we'll place the magnets close together with the opposite poles next to each other. Next, we'll place a piece of paper over the magnets and sprinkle some iron filings on the paper. Notice that the filings are forming patterns or lines. The lines that are formed by the filings indicate magnetic force lines. The lines are usually referred to as magnetic flux lines. Now, as we said, a magnetic field is one of the three elements necessary to create an electrical potential. Another element is a conductor. A good conductor is a substance that provides a path through which current can flow easily. Copper and aluminum are examples of good conductors. Natural rubber and synthetic rubber are examples of poor conductors. A poor conductor, or insulator, is a substance that allows little or no current flow. Insulators are often used around conductors to prevent current from taking undesirable paths. The third element necessary to create an electrical potential is relative motion between the conductor and the magnetic field. Let's see what this means. This conductor is a coil of copper wire. It's connected to an electrical sensing device. The pointer on this device will indicate an electrical potential. If we move a magnet through the coil, we'll be able to see the effects on the scale. Notice that as the magnet moves through the coil, the indicator swings alternately between positive and negative. If the motion stops, the indicator moves back to zero. The same thing will happen if the magnet is held stationary and the coil is moved around it. That's what relative motion means. Either the conductor or the magnetic field has to move. The electrical potential that's created in this situation is usually referred to as an induced electrical potential. The conductor, the magnetic field, and the relative motion induce an electrical potential in the conductor. This is the basic principle behind the generation of electricity that's used to operate equipment in industrial facilities. When an electrical potential or voltage is induced in a conductor that's part of a complete circuit, current flows through the circuit. In many applications, the current flows first in one direction and then in the opposite direction. Current that changes directions in this way is called alternating current. Let's look at an example to see how alternating current can be produced. This demonstration includes a conductor in a stationary magnetic field. The conductor isn't moving, so there's no voltage and no current. To make what happens easier to follow, we'll represent the changes in direction on a graph. One axis on the graph represents the induced voltage, and the other axis represents time. As the conductor rotates through the magnetic field in a clockwise direction, the induced voltage first builds up from zero to a peak or maximum value in one direction. We'll call that direction positive. As the conductor continues to rotate, the voltage returns to zero. It then changes direction, builds up to a peak or maximum value in the negative direction, and returns to zero again. At this point, the voltage has completed a full cycle. This curve is called a sine wave. Now, in an actual power system, cycles occur rapidly. In many cases, there are 60 complete cycles each second. The unit that represents cycles per second is hertz, so 60 cycles per second can be referred to as 60 hertz. The value of the induced voltage is at a peak 2 times during each cycle. Since the value of the voltage is continually changing, the peak voltage value is not the true or effective value of the voltage that's produced during the cycle. Instead, the effective voltage is an average value. In most cases, the average that's used is called the root mean square, or RMS value. The term root mean square refers to the mathematical method that's used to calculate the average of the different voltage values in a cycle. For simplicity, the RMS value is usually given as 0.707 times the peak value. That's accurate enough for most situations. Well, we've seen how AC voltage is produced and how it changes, and we've seen how these changes can be represented by a sine wave. The sine waves we've looked at so far are single-phase sine waves. They represent power produced by single-phase generators. However, most large industrial equipment operates using three-phase AC power. Let's take a look at what this means. In this illustration, the conductor consists of three equally spaced coils or loops. As these loops rotate through the magnetic field, each loop produces voltage that can be represented by a sine wave. This illustration shows the voltage sine waves for the three loops. You'll notice that even though at individual times each sine wave becomes zero, the sine waves are never zero for two phases at the same time. This means that the effective voltage and current produced by this three-phase arrangement are never zero while it's operating. In this topic, we learned about electricity. We discussed electrical potential and some sources of electrical potential. We also covered magnetism and alternating current. Now try a few practice questions to check what you've learned. The forces related to the movement of electrons can be referred to as electromotive forces, or EMF. EMF is one way of expressing electrical potential. Another term that is used interchangeably with electrical potential is voltage. A third source of electrical potential is light. Light may be a great source of electricity in the future. The principle of producing electricity by using light is referred to as the photoelectric effect. To make what happens easier to follow, we'll represent the changes in direction on a graph. One axis on the graph represents the induced voltage, and the other axis represents time. As the conductor rotates through the magnetic field in a clockwise direction, the induced voltage first builds up from zero to a peak or maximum value in one direction. We'll call that direction positive. As the conductor continues to rotate, the voltage returns to zero. It then changes direction, builds up to a peak or maximum value in the negative direction, and returns to zero again. At this point, the voltage has completed a full cycle. Basically, a motor is a device that uses electrical energy to produce mechanical energy. Let's use a demonstration to understand this better. This is a very simple example of an electric motor. It consists of two bar magnets and a rotor. The rotor is the part of the motor that moves or rotates. The two bar magnets which do not move are called the stator. Copper conducting wire is wound around the arms of the rotor. The rotor is connected to a shaft. In order to operate, the motor must be part of an electrical circuit. In this circuit, a battery is the source of electricity, and a switch is used as a control device. When the switch is closed, a complete path is formed, and current flows through the conducting wire. As you can see, the rotor is spinning, causing the shaft to rotate. The motion results from the interaction between two magnetic fields. One of the magnetic fields is produced by the bar magnets. We'll call this field the stator's magnetic field. The other magnetic field is the rotor's magnetic field. It is a result of the current passing through the conducting wire. Whenever current passes through a conductor, a magnetic field is created around the conductor. This type of magnetic field is called an electromagnetic field. If the shaft in this motor were connected to a mechanical device, it could be used to drive the device. Motors come in many different sizes and designs. The variations allow motors to be used in many different applications. Regardless of the particular design of a motor, however, the principle of operation is the same for all motors. That is, the rotor's magnetic field interacts with the stator's magnetic field, causing the rotor to rotate. Direct current, or DC, is current that flows in one direction. In a DC motor, direct current flows through a conductor and creates a magnetic field around the conductor. This magnetic field interacts with another magnetic field to produce motion. Let's look at a demonstration to see how a DC motor operates. The stator, or stationary part of this model, is a horseshoe magnet. The rotor, or rotating part, is simply a coil of conducting wire wound around a metal core. A battery supplies electricity to the motor. When current flows through the rotor's coil, it causes the rotor to become an electromagnet. The attraction and repulsion between the poles of the horseshoe magnet and the poles of the rotor cause the rotor to turn. During operation, the rotor must continuously switch polarity in order to maintain motion. In other words, the north and south poles of the rotor must switch. The parts of the motor that cause the poles to switch are a commutator and brushes. The commutator in this arrangement is a small copper conducting cylinder that is split into two halves. These two contact strips that touch the commutator are the brushes. When the motor is operating, current flows from the negative side of the battery through one of the brushes, then through one half of the commutator and onto the rotor. After the current flows through the rotor, it flows to the other half of the commutator, then through the other brush. And finally, it returns to the positive side of the battery. The commutator and the brushes constantly change the direction of current flow to the rotor. That's what changes the polarity of the rotor. Now let's take a look at how the commutator, brushes, and rotor windings cause a DC motor to work. This horseshoe magnet is the motor's stator. The north and south poles are indicated by the letters N and S. The poles of the rotor are indicated in a similar way. When the rotor is in this position, the north pole of the rotor is repelled by the north pole of the stator and attracted by the south pole of the stator. Similarly, the south pole of the rotor is repelled by the south pole of the stator and attracted by the north pole. The combined effect of these attractions and repulsions moves the rotor. At this point, the commutator and brushes switch the direction of current flow through the rotor coil. The change in current flow direction switches the polarity of the rotor. This change in polarity keeps the rotor rotating in the same direction. It continually moves toward opposite poles. This continuous process of switching polarity causes the magnetic fields in a DC motor to change positions. That's what causes a DC motor to operate. An AC motor operates because of the interaction between the magnetic fields of its rotor and its stator. In most AC motors, alternating current is supplied to the stator windings. The current flow causes the magnetic fields around the stator windings to increase, decrease, and change polarity. Let's look at an example to see how the magnetic fields of the rotor and the stator interact in a simple AC motor. These two coils of wire make up the stator. This bar magnet is the rotor. It has a north pole and a south pole. When current flows through the stator coils, magnetic fields are created around the coils. Each magnetic field has a north pole and a south pole. In our example, we're starting with the north pole of the rotor next to a stator north pole and the south pole of the rotor next to a stator south pole. The like poles repel each other, so the rotor starts to rotate. As it does, its momentum and the attraction of its poles to the unlike stator poles help the rotation to continue. When the alternating current flowing through the stator coils reverses direction, the stator poles reverse. As a result, the like poles are next to each other again. The like poles repel each other, and the rotor continues to turn. This sequence will continue as long as the stator windings are being supplied with alternating current. A three-phase AC motor is more complicated than the example we just saw, but the basic principle of operation is the same. The interaction between the magnetic fields of the rotor and the stator cause the rotor to turn. This illustration represents the stator of one type of three-phase AC motor. This stator has 6 coils. There are 2 coils, or 1 coil pair, for each phase of alternating current. The coils are connected through a common point in what is called a Y connection, or a star connection. In this arrangement, the coil pairs for each phase are 120 degrees apart from each other. As alternating current flows through each coil pair, magnetic fields are created just like they were for the simple AC motor we looked at earlier. However, since there are 3 coil pairs, the stator always has 3 north poles and 3 south poles. As current flow through each coil pair increases, decreases, and changes direction, Each magnetic field increases, decreases, and changes polarity. Because the coil pairs are 120 degrees apart from each other, the net effect through the complete three-phase cycle is that the overall magnetic field between the stator coils rotates.